In this video we will demonstrate the peak deconvolution function of Topspin. Spectrum deconvolution is a mathematical method used to simulate a region of a spectrum to give details of chemical shifts, line widths and integral intensities. The algorithm is robust enough to be able to separate peaks that have significant overlap. Let's first look at what makes NMR lines difficult to integrate and get accurate quantitative results. In theory, and extensively in results, NMR resonances have a shape that follows a Lorentzian function. This shape is characterized by a sharp top but a very broad baseline that tails off for a long distance from the center. For this reason, a very wide integral region is needed to measure the area of a resonance. To measure 95% of a Lorentzian peak's area, the width of the integral region needs to include 6 times the line width at half height on both sides of the peak. Typical NMR lines have about a 1 Hz line width, but many peaks are broader. For multiplets, this area starts from the outer lines and the total region needed can become quite large. To measure 99% of the peak's area, the integral region has to span almost 50 times the peak width. In many spectra, with peaks closely spaced, this is not possible and deconvolution should be used if you require accurate peak intensity measurements. Let's look at a series of simulated examples that show how integration of two closely spaced peaks can be problematic. These examples show actual output of the deconvolution routine of Mestra Labs M-Nova NMR processing software. Similar results can be produced in Topspin, and we will look at a couple of examples on real data later in this video. In the simulation we have two Lorentzian-shaped peaks with 1 Hz line width separated by 0.01 ppm. This simulation was set for a 400 MHz instrument, therefore the peaks are 4 Hz apart. For the first case we have set the intensities to the same value so the tailing of each peak affects the other equally. If you integrate the peaks by cutting the two regions at the minimum between the two lines you can get an accurate measurement of the relative peak areas. The deconvolution result for this example is shown here. The two individual component lines can be seen in the result. There is also a summed trace that is overlapped with the initial spectrum. The numeric results are shown in the table above the spectrum. This contains the deconvolution line's chemical shifts, line widths and integral intensities listed as area. In this case, the areas are calculated as equal. For the next example the intensities are set to have a 2:1 ratio. If we cut the integration regions at the minimum between the two lines we get values that are close to the actual intensity ratio. However, the minor peak's area is overrepresented by about 5%. In this, and following examples we are setting the major peak intensity to the inputted value and observing the error introduced in the minor's measured value. However, you can also consider the error to include the loss of intensity of the major peak since we cannot fully integrate its intensity. The deconvolution results yield the accurate relative peak areas. The calculated traces extend into the region of the adjacent peak and includes the full peak intensity. The next case is a 4:1 intensity ratio, and the integration is introducing much more error. Here the minor peak is showing over 15% error, but remember the measurement of the major peak is also being affected even if the set value shown here is 4. The summed area of the two peaks should be 5, not 5.16 shown here. The deconvolution result for the 4:1 case is still accurate and the areas yield the correct ratio. We will finish the series with peaks set to a 10:1 ratio. The integration results are now showing about a 40% error for the minor intensity. However, the deconvolution again has no problems determining the accurate area ratio. Hopefully this example has convinced you that the only way to get accurate intensity measurements for closely spaced NMR resonances is to use spectrum deconvolution. Here are some guidelines that you should consider before you attempt to use the deconvolution routine. First, the spectrum should be well shimmed. Deconvolution fitting produces symmetric peaks, so your experimental peaks need to be as symmetric as possible. This requires good shimming, and remember good shimming requires good clean samples. Make sure your samples have the correct solvent height and are filtered from any floating particles. Exponential line broadening can help, but it is not a substitute for good data. The spectrum should have good signal to noise. This will help the simulation fit the peak baselines. Use some extra line broadening if necessary. The phasing of the spectrum is critical. Take extra care adjusting the phase because the routine will not fit poorly phase lines very accurately. The spectrum also needs a good baseline. Run the BAS command before you start the deconvolution routine if the baseline does not sit level at zero intensity. Let's look at a couple of examples in Topspin. Our first spectrum is of N-methylformamide. This planar molecule exists in two rotational forms, where the trans has a significantly higher abundance. The exchange rate is slow at ambient temperature and we see resonances from each form. The proton on the nitrogen is labile and rapidly exchanges with the solvent OH, which was deuterated methanol. The peaks near 8 ppm are from the formamide protons. Moving upfield we next find a peak that is from the labile protons, which can also include any free water. The residual methanol peak shows at 3.3 ppm. We can expand into the region that includes the methyl resonances for the major and minor forms. Expanding the vertical scale shows the C13 satellites of the major rotamer and an unknown impurity. As you can see, one of the C13 satellites overlaps the minor methyl peak, making integration impossible for determining the ratio of the two forms. When you perform deconvolution, you want to expand into regions of just the peaks you want to include in the calculations, but you also want to give an area of baseline on either end of the range. You should examine the spectrum to make sure the lines are symmetric and the baseline is at zero on the y-axis scale. As you can see, there is slight tailing on the major peak to the right or upfield side, and this will cause some problems with the deconvolution. We can mask this by applying a little extra line broadening, more than you would use for normal results. In this case we will change the line broadening to 1 Hz and reprocess the spectrum with the EFP command. Note that the overlap between the minor rotamer and the C13 satellite of the major form has more overlap due to the imposed larger line widths. The deconvolution should be able to handle this. The major peak shows less tailing and this will lead to better deconvolution results. The baseline and spectrum phasing both look good, so now we can move on to deconvolution, with the goal to get the relative intensities of the two forms. To enter the deconvolution routine, you would select the Analyze option from the main menu at the top of the Topspin window. Then open the pull-down menu for line shapes on the flow bar. Select the top option, Fit Lorentzian/Gaussian functions. You could also type Dcon at the command line to enter the routine. Notice how the flow bar changes to reflect the options for the deconvolution steps. It is laid out to work with from the left to the right. The first step would be to click on the Destination button. This will define the processing sub-folder where the deconvolution results will be written into. The default is always 999, and the only reason to change this is if you want to compare different results. You can confirm the default by clicking the OK button. Next you would click the Define Peaks button. This opens the manual peak picking routine. The peak picking from earlier will be carried over into this routine, so you should examine what peaks are selected and remove the ones you do not need. Since we are only interested in the two largest peaks, we will first remove all the peaks with the icon with the red X, then use the bracket selection tool to select the two methyl peaks. We will soon see that the choice of just including the peaks of interest is not the correct decision, but let's review the results. With the peaks selected, we would then click on the button with the D icon. This option is to save the peak list and start deconvolution. When this button is selected, a dialog box opens. This shows a table with the selected peaks that includes the frequency in Hertz, the starting line widths and a column that show the % Gaussian. We will see why and how to use this option later in this video. The dialog box confirms that we have selected two peaks. The next step is to click on the Start Deconvolution button at the bottom of the window. The initial thing you will see is a window with the results shown in a numeric table. The columns show the calculated frequency, or chemical shift in both Hertz and ppm. Next is the calculated line widths in both Hertz and ppm. The column labeled intensity is actually the height of the peaks. The column labeled area is the integral intensity. The last column displays the % Lorentzian and the chi-squared value, which is a measure of the fitting error. The rows display the two peaks we selected. Before we use this information, we first want to examine the fitting in the graphics window, which is behind the text window. This is Topspin's multi-display mode, which allows displaying and manipulating more than one spectrum. Please watch our earlier video on multi-display mode for an introduction on how to use this part of the program. Graphically is probably the easiest way to judge how successful the fitting was performed. The blue trace is the experimental data, and red is the calculated output of the deconvolution routine. The first thing you will notice is that both peaks of the calculated result were truncated at the outside limits. This is a long-lasting and frustrating bug in Topspin. It is unclear if the numeric results are affected by this bug or not. However, the truncated peaks make it difficult to visualize the success of the fit. If we rerun the deconvolution and include peaks outside the area with the two peaks we are interested in, it will push the software bug off the peaks we want to quantify. So, let's exit multi-display mode and go back into define peaks. Using the manual peak picking tool, we are going to add peaks that outflank the peaks we are interested in. This could be a real peak or just noise. In this case, I am selecting the C13 satellite of the minor peak at the left. I will also add the C13 satellites of the major component as well as the impurity peak up field of the region, which, while I am not interested in measuring, it will give a good border for the truncation bug. When done, we will choose the D button to open the dialog box. The list now includes all 6 peaks we selected. We can then perform the deconvolution by clicking on the Start Deconvolution button. Again, the text window opens with the numeric results. The first 2 rows and the last 2 rows are the peaks we added, and the middle 2 rows are the peaks of the minor and major rotamers that we are interested in. Let's take a look at the traces in the multi-display mode. The truncation is not as severe as before and all 6 peaks are showing reasonable fits, but to get a better look we can overlay the spectra. It is apparent that the red calculated trace has a wider base than the experimental blue spectrum trace. Notice that while the middle of the peak looks well fit, the top shows a poor fit as well. This lack of success in the fitting is because we have limited the deconvolution to just a Lorentzian line shape. While all NMR peaks theoretically have Lorentzian shapes, there are occasions where the peaks display some Gaussian characteristics. This can be due to a slow chemical exchange process like we have here. It could also show in peaks that arise from a heterogeneous structure like a polymer, where a resonance is actually a distribution of many different peak positions. Gaussian peaks are much narrower on the bottom compared to a Lorentzian shape of the same half-height line width. They are also rounder at the top. Sometimes it is necessary to mix in some percent of Gaussian shape to achieve the best fit. To do this, we have to exit multi-display mode and re-enter the define peaks for the manual peak picking mode. Now click on the D button to bring up the deconvolution entry box. Notice that the third column has a listing of the percent Gaussian. This table can be edited to introduce a fraction of Gaussian into each line. We will only add this to the 2 lines we are interested in. We recommend starting at 50%, or 0.5, and adjusting as necessary. Next, start the deconvolution and exit the numeric results to examine the fit. This overlap is pretty good, and it is better than using a pure Lorentzian line shape. We can closer examine the fit by looking at the difference between the experimental and the calculated results by clicking on the button with the delta icon. The green trace is the difference between the 2 other traces. There are some small differences, but this is actually a pretty good fit and probably the best this dataset will give. We can now bring back the numeric results table by clicking on the View Fit option in the flow bar and choosing View Numeric Results. From here we can use the peak areas to determine the ratio of the 2 forms, which comes out to 15.8 to 1. The View Fitted Shapes option in the pull-down can give you a cleaner view of the calculated traces. This shows the individual traces and the sum of all the lines. Notice it does not have any of the ugly truncation that the multi-display mode shows. We assume that these results are used for the numeric values and the truncation is just a graphic artifact. However, we cannot be sure, so we advise people to include the outer unwanted lines in all calculations. Our next example is a spectrum of 2,2-difluoroacetic anhydride in which part of the sample has been hydrolyzed to the free acid. The spectrum shows the free acid proton at around 11 ppm. The sample was run in deuterochloroform and the residual proton shows up at 7.28 ppm. At around 6 ppm are the protons on the difluoroacetate carbon. These protons are both triplets due to coupling with the F19 and they are highly overlapped. To determine the extent of hydrolysis we could integrate the acid peak against these protons. However, the line width of the acid proton is pretty large and there could be relaxation differences. The more challenging option would be to compare the intensities of the two triplets. For that, deconvolution would be the best option. The spectrum looks like it is well shimmed and phased. The baseline also looks good, so we can start the deconvolution routine by clicking the Analysis menu and choosing the Line Shapes pull-down menu and then fit Lorentzian/Gaussian functions. Then click on Destination and click OK on the default processing location. Next we click on the Define Peaks to bring up the manual peak picking interface. The previous peak picking has selected all of the peaks we are interested in. The small peak to the left looks good to use as a flanking peak. We can manually add a small peak to the right that is a little further away from the peaks we want. Now we can click on the button with the D icon to show the list of peaks selected with the peak picking. Then we can perform the deconvolution with the Start Deconvolution button. The numeric results window opens and shows quite a few lines. Let's first look at the fitted results in the multi-display mode. As you can see, the Lorentzian fits are an excellent representation of the experimental dataset. The difference between the calculated and experimental spectrum shows good agreement. We can bring back the numeric results to add the 3 peaks for each triplet to determine total area for the anhydride in free acid. Then we could compare the totals to determine the percent of hydrolysis. This came out to 13.4%. This concludes our video on NMR spectrum deconvolution. The routine in Topspin has some issues but it can yield very good results. It lacks some control of the starting input and it will not optimize the Gaussian to Lorentzian shape ratio, so you have to manually make changes and rerun the fit. The deconvolution routine in MNOVA is superior to Topspin and we recommend it if you have a lot of spectra to simulate or if your spectra include broader line widths. However, MNOVA is not free and the cost might be prohibitive for some research groups. Mestra Labs allows downloading a demo version so you can test the program for your project before you commit to purchase. Please see the staff for assistance with using the deconvolution routine in Topspin or if you have any questions about MNOVA's capabilities. Thanks for watching.